In this video, we'll be talking about geometric sequences, and specifically when a geometric sequence might converge to a specific number. So, first off, let's define a geometric sequence. A geometric sequence is any sequence such that it appears in some form like this. You may also see it like this. A sub n is equal to simply r to the power of n. You may simply see it as a sub n equals r to the n minus 1. And again, this one right here, such that we have a leading term, or a sub n equals a r to the n minus 1. Any one of these forms is really a geometric sequence. It's important to note that this is probably the most basic form of a geometric sequence you might see. The reason for a geometric sequence is specifically one that for every single term you have, whatever term it has been multiplied by a specific value a certain number of times. Generally either equal to the term number it is, or sometimes in cases one less than the term number it is. So a basic geometric sequence might be a sub n equals to 1/2 to the power of n. So if I try to plug in 1, this is going to just simply be 1. If I plug in 2, then I'm going to have 1/4 times 2, which is simply 1/2. And you'll notice that as I plug in values, the numbers in this particular sequence continue to get smaller and smaller. Again, this is more like just 1, 1/2, then 1/4, and so on and so forth. Now, let's discuss the concepts of when a geometric sequence will diverge or will converge. So when we define a geometric sequence, we define a geometric sequence such as this. Now, in Algebra 2, we would define it in such a way that R specifically has to be not 1, and it has to be greater than 0. Now, this is not necessarily true when we talk about it in terms of calculus. In terms of calculus, this is a geometric sequence for any R value. Now, we do end up talking about for what R values does it converge. So let's go through all the possible R values. Let's first start off with the most common one. If I have a sub n is equal to r to the power of n, such that r is greater than 1. If r is greater than 1, the concept is that if the number that I plug in for r is, say, 2, 7, 12, any number larger than 1, then as I plug in n values that get larger and larger, I plug in 1, and then I plug in 2, and then I plug in 3, and then I plug in 4, the r to the power of n is going to get exponentially larger. So in that case, this right here, if r is greater than 1, then the geometric sequence diverges. Okay, and again, diverges is the way of stating that the sequence either increases or decreases without bound, going off to infinity, or it bounces back and forth uncontrollably, again, oscillating. Now, what if we talk about r equals to 1? Well, if r equals to 1, then this sequence simply becomes a sub n equals 1 to the n. Well, 1 to the n is nothing more than just a bunch of 1s in that specific order. So what we would say there is that this is obviously converging. This is a geometric sequence that is converging. And it's converging specifically because, well, it's the sequence of all 1s. It converges to the value of 1. As n gets larger, the sequence does approach 1. The last case we have is, well, what if r is less than 1? Now, the part that's off about this is that I can use greater than 1, I can use equals to 1, but when I start talking about r is less than 1, again, keep in mind that in Algebra 2, we might say that r had to be greater than 0, but in this class, it doesn't have to be. So what I'm going to say here is that technically I should be going all the way through this to -1. Okay, now the reason why I have to do all of the values in between is because if I plug in a fraction to this, a sub n, and we're going to use this as an example, I have 1/2 to the power of n. What happens is I continue to plug in 1. Well, 1 gives me 1/2, again 2 gives me 1/4, 3 gives me 1/8, and so on and so forth. And the overall values of this are getting smaller and smaller. So for this particular case, as r is between -1 and 1, this again works for 0. If I had a 0 here, and to the 0 to the power of n any number of times, it's still going to be 0. So this thing overall, the geometric sequence will converge, and specifically it will converge to 0. So in that case, we have geometric sequences greater than 1. I should add to this piece up here, what if r is less than a -1? What if I'm on the opposite side over here of the values between -1 and 1? So between -1 and 1, I have convergency. At 1, it converges. At -1, well, what would happen if I plugged in -1? This thing would bounce back and forth between 1 and -1 and 1 and 8. I don't know that at -1 this thing would actually converge. It might be arguable that a sub n is equal to -1 to the power of n is actually equal to -1, 1, -1, 1, -1, 1, and so on and so forth. So I would argue that this particular sequence right here, such that r is a -1, that one would also diverge. So, with this statement being said, anything that's less than -1, again being large values, would also diverge. Anything that's 1, just 1, would converge. Anything between -1 and 1 would also converge. So the argument really here is that a sub n equals a r to the n of any form, again of any form, will converge when r is less than or equal to 1 or less, greater than -1. So that covers the concepts of how a geometric sequence might converge or diverge, and we'll use this in videos to come.